what are we up to? Previously, so we just finished talking about a couple of advanced counting techniques, namely recurrence relations and how to solve them, as well as our upgraded inclusion-exclusion principle for more than two sets. Now we're going to start another new topic, which is relations. So this is getting back to some of the more general abstract stuff we were doing at the beginning about sets and functions. So it's going to be a similar flavor to that kind of work. The relations are, maybe can be, well, maybe not too much mercifully, but it'll get a little bit abstract. Well, let's go ahead and do it. So let me give a definition. So a relation R on a set A is quite simple. It is just a subset of the Cartesian product of A with itself. So it's a set of ordered pairs of two elements of A. And let me just say as an aside, you can also define a relation from A to another set B, which is a subset of A cross B. But we will not talk about this because almost always you are worried about relations on a set or from a set to itself, you could say. So they're going to be subsets of A cross A. And relations, like I was saying, like sets and functions, is really ubiquitous in math. So it's a foundational tool in any context where sets are used, which is everywhere. So they really show up a lot of places. So let me say something about what this definition is saying. So it's a subset of this direct product, but that's kind of an abstract way of saying it. What does that mean? It's the subset of pairs x comma y, where x is related to y. So we have some relationship between elements of our set, and we're just recording this relationship by writing down all the pairs of elements that are related in this way. And just as some additional notation, it's sometimes convenient to write, instead of ordered pairs, something like x, r, y, to mean that this ordered pair is a member of this relation. And you can also write x not r, y, to say that x, y is not in this relation. So let's see some examples. So let's take a set A, which is 2, 3, 4, 5, 6. So a couple of numbers. And R, subset of A cross A. The relation defined by xy is in R, or which is to say x is related to y, if x divides y. So you can see that there is sort of plenty of abstraction that we're using to make these definitions, but the idea is is fairly simple in this example, that we're just thinking about the relationship of one number dividing another. So I will stop doing this almost immediately, but in this case, let's be super explicit and write down R out as a set, all its elements. So what are the numbers in this set that divide other numbers in this set? So 2 divides 2, so let me write it like this. You can see that, so this notation is a mirror of this notation. So you can see that's one way it's used. But you can also write it as ordered pairs, which is what I'm going to do in this example for this explicit writing it down. So 2 divides 2, 2 divides 4, 2 divides 6, and then 3 divides 3, and 3 also divides 6. And then all the rest is just 4 divides 4, 5 divides 5, and 6 divides, I keep wanting to write the divide sign. 6 divides 6. Okay, so this is our relation, and here are all of its elements. It's a subset of the Cartesian product of A with itself. And also, you know, for example, 2, 5 is not in R because 2 does not divide 5. Very good. So often it's clearest not to write down the relation at all and just to use properties that you know about it to work with it. But if you want to visualize things, there's a couple ways that you can diagram it. Let me write that down. So it can diagram in a couple of ways. One way, which maybe we can call function style, is to write the elements of your set as dots on both sides. And then, just like you're drawing a function, you draw arrows whenever that element is related to that element. So 2 is a divisor of 2, so we get that arrow. It is also a divisor of 4, so we get this arrow. And of 6, so we get that arrow. And then 3 divides 3, and 3 also divides 6. And 4 divides 4, 5 divides 5, 6 divides 6. So you get a big, messy diagram like this, but it encodes very clearly all of the information of your relation. Then you can also use the tabular style, let's call it. So here you write it as a table. So let's write the elements of our set along these 2 coordinates. And let's say that this left-hand side is the first coordinate, and the top-hand side is the second coordinate. So first and second in terms of these ordered pairs. So since divisibility is not the same both ways, which we'll get to that in a moment, it matters which you choose to be the first and which you choose to be the second. So 2 divides 2 means that this box gets a check. 2 divides 4 means that this gets a check, and 2 divides 6, and then 3 divides 3, and 3 divides 6, and 4 divides 4, 5 divides 5, and 6 divides 6. I believe that is what it looks like. Right, very good. So here is one small example of a relation on this set with 5 elements in tons of depth. Let's introduce just a couple more examples that we can keep in mind when we talk about the next couple of things. So let's consider the relation on the integers given by congruent mod 5. So we are saying that, let's write it like this. R is equal to the ordered pairs in z cross z, such that x is congruent to y mod 5. So this is a relation, and it's one that we will be talking a lot about. And a couple more that we'll talk a lot about. I'm not going to use consistent naming for these, so I'll go ahead and reuse the name R. These are relations on the real numbers, or indeed on the integers or various other things. So we can define relations by less than equal and less than. So again, to be precise, R is the set of ordered pairs x, y, of real numbers this time, such that x is less than or equal to y. And S, you can think about the set of ordered pairs of real numbers where x is less than y. So these are all examples of relations. And next, we will talk about some important properties that relations can have.